Look up at the night sky. What do you see? Stars, planets, maybe the faint glow of the Milky Way. For thousands of years, we have stared into this vast darkness and wondered what it all is. We've built incredible tools, from giant telescopes that see across billions of light years to powerful microscopes that peer into the heart of an atom. We have learned so much. We know that everything we see, from the largest galaxy to the smallest grain of sand, is made of tiny, fundamental particles. These are the building blocks of reality. It's a beautiful, elegant picture of the universe. But there's a catch, a very big one. The universe we can see, the one made of stars, planets, and us, is only a tiny fraction of what's actually out there. It's about 5% of the total cosmic pie. The rest is something else. We call it dark matter and dark energy. For the last 50 years, physicists have had a remarkable theory to describe the fundamental particles and forces of nature. It's called the Standard Model of Particle Physics. You can think of it as our best and most detailed map of the subatomic world. And it is stunningly successful. It describes how a small handful of elementary particles interact with each other to build everything we know. It tells us about quarks, which combine to make protons and neutrons inside atoms. One of the most mysterious residents of the Standard Model is a particle called the neutrino. There are 3 known types or flavors of neutrinos, and they are everywhere. Trillions of them are streaming through your body every single second, produced by the nuclear reactions burning in the heart of the sun. But you don't feel them. They are incredibly elusive, interacting so weakly with other matter that they can pass through the entire Earth without hitting a single atom. For this reason, they are often called ghost particles. For decades, we thought they had no mass at all. Then we discovered something astonishing. Neutrinos can change. As they travel through space, they can morph from one flavor into another, a phenomenon called neutrino oscillation. To understand the search for missing particles, we first need to ask a very basic question. What is a particle? Imagine you have a Lego brick. You can use it, along with other bricks, to build a house, a car, or a spaceship. Now imagine breaking that Lego brick in half, and then in half again, and again. If you could keep going, you would eventually reach a point where you couldn't break it down any further. You would be left with something truly fundamental, something that isn't made of anything smaller. This is the basic idea behind an elementary particle. They are the ultimate, indivisible Lego bricks that the universe uses to build everything we see around us. These fundamental particles are a very exclusive club. The Standard Model, our inventory of the universe's building blocks, tells us there are only a handful of them. They are organized into groups, a bit like a family tree. First, you have the quarks. There are 6 types with whimsical names like up, down, charm, and strange. Having a set of building blocks is one thing, but you also need instructions on how to put them together. Quarks and leptons don't just randomly float around. They talk to each other. They push and pull on one another. These interactions are what we call the fundamental forces of nature. The Standard Model doesn't just list the particles of matter. It also describes the particles that carry these forces. You can think of them as messengers, constantly flying back and forth between the matter particles, telling them how to behave. These force-carrying particles are collectively known as bosons, and they are the glue that holds the universe together. The Standard Model, with its neat families of quarks, leptons, and bosons, is a triumph of science. It explains almost everything we see and measure in our particle accelerators. So, you might ask, if the theory is so good, why are we so obsessed with finding what's missing? The answer is simple. Because the Standard Model, for all its success, leaves the biggest questions about our universe completely unanswered. Think about dark matter. We know from observing galaxies that about 85% of the matter in the universe is something invisible that doesn't interact with light. We can look through our entire list of Standard Model particles, all 17 of them, and not a single one has the right properties to be dark matter. Our story begins in the early 20th century, with a deep puzzle in the world of physics. Scientists were studying a process called beta decay, where an atomic nucleus spontaneously spits out an electron and transforms into a different element. When they measured the energy of the electron that came flying out, they found something deeply troubling. One of the most sacred laws of physics, the conservation of energy, seemed to be violated. But one brilliant physicist, Wolfgang Pauli, had a different, more radical idea. In 1930, he wrote a famous letter to his colleagues, cheekily addressed to the dear radioactive ladies and gentlemen, proposing a desperate remedy to save the law of energy conservation. Pauli suggested that the energy wasn't missing at all. Instead, it was being carried away by a new, undetected particle. For 26 years, the neutrino was nothing more than a ghost in the theory. Many scientists doubted it would ever be found. I mean, how could you possibly detect a particle that could travel through light years of solid lead without hitting a single thing? But two American physicists, Frederick Rines and Clyde Cowan, were determined to prove that Pauli's ghost was real. They found their source in a place that represented the cutting edge of technology in the 1950s, a nuclear reactor. Their experiment, conducted at the Savannah River plant in South Carolina in 1956, was a masterpiece of experimental physics. After months of careful data collection and analysis, they finally found what they were looking for. They observed the telltale double flashes of light at the exact rate predicted by theory if neutrinos were real. They had done it. They had caught the ghost. They sent a telegram to Wolfgang Pauli to inform him that his desperate remedy from so many years ago was not just a clever idea, but a physical reality. The discovery of the neutrino was just the beginning of the story. As physicists delved deeper into the subatomic world, they found that the neutrino family was more complicated than they first thought. In the 1960s, experiments revealed that there wasn't just one type of neutrino. For many years, we thought there were just these two. But the Standard Model, in its elegant symmetry, predicted that there should be a third lepton, the tau particle, and that it too should have its own neutrino partner. Finally, in the year 2000, at the Fermilab accelerator near Chicago, the tau neutrino was directly observed, completing the trio. Scientists studying neutrinos coming from the sun noticed something very strange. They were detecting far fewer electron neutrinos than their models of the sun predicted. The solution to this puzzle was revolutionary. The neutrinos weren't disappearing. They were changing. As they traveled from the sun to the Earth, the electron neutrinos were morphing into muon and tau neutrinos, flavors that the early experiments weren't designed to detect. The discovery of neutrino oscillations was a monumental moment in physics. It proved that neutrinos have mass, a property the Standard Model in its simplest form said they shouldn't have. This immediately raised a new profound question. Where does this mass come from? This puzzle has led to a fascinating idea. What if there is a fourth type of neutrino, one that is even more ghostly than the others? This hypothetical particle was given the name sterile neutrino. The name is wonderfully descriptive. So how could an invisible particle solve the puzzle of neutrino mass? The leading theory is called the seesaw mechanism. The mathematics of this partnership works like a child's seesaw. If one side goes up, the other goes down. The immense mass of the sterile neutrino on one side of the seesaw forces the mass of the active neutrinos on the other side to be incredibly tiny, which is exactly what we observe in our experiments. The idea of a sterile neutrino is beautiful, but is there any actual evidence for it? The search for this phantom particle has led scientists to look for tiny anomalies, subtle hints in their data that don't quite fit the standard 3-neutrino picture. One of the first intriguing clues came from an experiment at the Los Alamos National Laboratory in the 1990s called the Liquid Scintillator Neutrino Detector, or LSND. A follow-up experiment called Mini-Boon at Fermilab was designed to check the LSND result. For years, its findings were ambiguous, sometimes agreeing with the anomaly, sometimes not. Other clues have come not from particle accelerators, but from looking out into the cosmos. Some physicists have proposed that sterile neutrinos could be a component of dark matter. Astronomers have scoured the skies, looking for a faint glow of X-rays that could be produced when these sterile neutrinos occasionally decay. If sterile neutrinos are ever definitively discovered, the implications would be enormous. It would be the first particle found that does not interact with the strong or weak nuclear forces, or with electromagnetism. This would shatter the neat and tidy structure of the Standard Model. It would prove that there is a sterile sector of particles that exist alongside our own, interacting with us only through gravity, and perhaps through very subtle mixing with known particles. The discovery could also solve some of the deepest puzzles in cosmology. As we've seen, certain types of sterile neutrinos are excellent candidates for dark matter. Furthermore, sterile neutrinos could help us understand one of the most fundamental questions about our existence. Why is the universe made of matter at all? Their existence could literally be the reason we exist. The search for the sterile neutrino is therefore more than just a hunt for another particle. It's a quest for a deeper understanding of reality itself. Our journey into the hidden universe now takes us to another profound puzzle, one that originates deep within the heart of the Standard Model itself. This isn't about a missing force like gravity, or an unexplained observation like dark matter. This is a problem with one of the forces we thought we understood very well, the strong nuclear force. The equations allow for a particular kind of asymmetry, a violation of a rule known as charge parity or CP symmetry. This asymmetry is seen in the weak force, so we expect to see it in the strong force too. The problem is we don't. When physicists perform incredibly precise experiments to look for this expected asymmetry in the strong force, they find nothing. Absolutely nothing. It's as if nature has a dial that could be turned to any value, and for some unknown reason, it has been set precisely to 0. This isn't just a small discrepancy. The strong force is at least 10 billion times more symmetrical than the theory suggests it needs to be. This mystery is known as the strong CP problem, and it has been a thorn in the side of particle physics for decades. The Peche-Quinn theory elegantly solved the strong CP problem on paper, but it came with a fascinating consequence. A few years after the theory was proposed, physicists Frank Wilczek and Steven Weinberg independently calculated the properties of this hypothetical particle. Wilczek decided to name it the Axion after a brand of washing detergent, because it was a particle that cleaned up a messy problem in the theory. According to the theory, the Axion would be a truly remarkable particle. It would have no electric charge and would be incredibly light, potentially millions or even billions of times lighter than an electron. More importantly, it would interact with other particles extremely weakly, even more weakly than neutrinos. This is why we haven't seen it yet in our powerful particle accelerators like the Large Hadron Collider. The beauty of the Axion idea is that it doesn't just solve the strong CP problem, it does so in a dynamic and natural way. You can think of the whole system like a ball rolling down into the bottom of a valley. The Peche-Quinn mechanism provides the valley, and the Axion is the particle that allows the system to roll down to the lowest point, which corresponds to 0. Once it's there, it stays there, ensuring the strong force remains symmetrical, just as we observe. For many years, the Axion was considered a clever but niche idea, a theoretical curiosity mainly of interest to physicists thinking about the strong force. But then, a completely different field of science, cosmology, realized something incredible. This very same particle, the Axion, proposed to solve a fine-tuning problem in particle physics, also happens to have all the right properties to be the elusive dark matter that astronomers had been searching for. How could this work? The theory predicts that in the chaotic aftermath of the Big Bang, a vast number of axions would have been created. Not from heat, but from the oscillations of the axion field itself as the universe cooled and expanded. These axions would have been created with very little motion, making them cold dark matter. They would then have spread throughout the cosmos, forming huge invisible clouds or halos. Over billions of years, the gravity from these axion halos would have pulled in ordinary matter, providing the cosmic scaffolding needed for galaxies like our own Milky Way to form and hold together. This makes the axion a perfect dark matter candidate. It is stable, so it wouldn't have decayed away over the age of the universe. It has no electric charge, so it doesn't interact with light, making it completely dark. So how do you hunt for a particle that is defined by its ability to hide? Searching for the sterile neutrino is one of the greatest challenges in modern experimental physics. Since it doesn't interact through the weak force like its active cousins, we can't use the same methods that first detected neutrinos at nuclear reactors. Instead, physicists must look for its subtle influence on the particles we can see. The main strategy is to search for tiny anomalies in neutrino oscillations. To do this, scientists have built a new generation of incredibly precise experiments. At Fermilab in the United States, a suite of 3 liquid argon detectors, The short baseline neutrino program is positioned at different distances from a powerful neutrino beam. By comparing the neutrino data at each detector, scientists can search for the telltale signs of neutrinos disappearing into a sterile state and then reappearing. The stakes are incredibly high for these experiments. Finding evidence of a sterile neutrino would be a revolutionary discovery, our first glimpse of a particle from a hidden sterile sector. The search for the axion requires a completely different and arguably even more ingenious strategy. Axions are not expected to be produced in large numbers in our accelerators. Instead, if they form the dark matter of our galaxy, we should be swimming in a sea of them right now. However, theory predicts one very specific, very weak interaction. In the presence of a strong magnetic field, an axion can, on very rare occasions, convert into a particle of light, a photon. This principle is the basis for the most promising type of axion experiment, known as an Axion Haloscope. The most famous of these is the Axion Dark Matter Experiment, or ADMX, at the University of Washington. At its heart, ADMX is a very sophisticated and sensitive radio receiver. It consists of a large, hollow metal cavity placed inside the powerful magnetic field of a superconducting magnet. The signal from a single axion converting into a photon is unbelievably faint. It is less than a yoctowatt, a millionth of a trillionth of a watt. To detect such a tiny signal, the entire experimental apparatus must be cooled down to temperatures just a fraction of a degree above absolute zero. The experiment then works like tuning a radio. Scientists slowly and meticulously adjust the resonant frequency of the cavity, listening for a tiny excess of power at one specific frequency that would signal the discovery of the axion. While oscillation experiments and haloscopes are the leading strategies, scientists are, well, a creative bunch, and are pursuing many other avenues to find these hidden particles. For axions, one alternative method is the so-called light shining through a wall experiment. Another clever idea, known as an Axion Haloscope, points a powerful magnetic telescope directly at the sun. For sterile neutrinos, the search is also expanding. Besides the accelerator-based experiments, some projects are looking for the faint signature of decaying sterile neutrinos from the cosmos. Telescopes that can detect X-rays, like the Chandra X-ray Observatory, are used to carefully study the light from massive objects like galaxy clusters, looking for a telltale, unexplained spike in the X-ray spectrum at a specific energy. The future of the hunt lies in bigger, more sensitive machines. The proposed DUNE, Deep Underground Neutrino Experiment, in the United States will have detectors far larger and more capable than current experiments, offering unprecedented precision in studying neutrino oscillations. For axions, new projects are being designed with stronger magnets and larger cavities, capable of scanning for the particle faster and with greater sensitivity. Each new generation of experiments builds on the last, pushing into unexplored territory. We stand at a remarkable moment in the history of science. Our current map of the universe, the standard model of particle physics, is a masterpiece of human intellect and curiosity. It has guided us through the subatomic world with incredible precision, explaining the fundamental building blocks of everything we can see and touch. Yet, we find ourselves staring into the dark, knowing that our map is incomplete. The very existence of galaxies, the strange behavior of ghost-like neutrinos, and the unnerving perfection in the laws of nature all tell us the same thing. There is more out there. There are hidden corners of reality we have not yet explored, populated by particles we have not yet met. This is what makes science so profoundly exciting. It's not about having all the answers. It's about the relentless, joyful pursuit of the next question. The search for sterile neutrinos and axions is the embodiment of this spirit. These are not just fanciful ideas. They are compelling, elegant solutions to some of the deepest puzzles we face. Why does this search for tiny, invisible particles truly matter? It matters because finding even one of them, a sterile neutrino, an axion, or something else entirely unexpected, would ignite a revolution in science. It would be more than just adding another particle to the chart. It would be the first definitive, concrete piece of evidence for physics beyond the standard model. Imagine the moment we confirm the existence of the axion. We would suddenly understand that the invisible dark matter holding our galaxy together is not some exotic, heavy particle, but a vast cosmic field of incredibly light, ghostly particles, a relic from the first moments of the Big Bang. Or consider the discovery of the sterile neutrino. This would prove the existence of a hidden sterile sector, a whole family of particles that barely interacts with our own. The discovery would usher in a new era of physics, providing the first signposts on the path toward an ultimate theory that unites all forces and particles into a single, elegant description of everything. It is a revolution in waiting. So, what comes next? The hunt continues with more passion and ingenuity than ever before. Experiments are growing larger, more sensitive, and more creative. Every year we get closer. We rule out more possibilities for where these particles could be hiding, narrowing the search and refining our aim. We are closing the net. This quest is fundamental to what it means to be human. Since our earliest ancestors looked up at the stars, we have been driven by a profound curiosity about the world around us. We have an innate desire to ask questions, to explore, and to understand. The search for hidden particles is the modern expression of that ancient impulse. And even if these particular searches for sterile neutrinos and axions come up empty, the quest will not end. The hidden universe is calling to us, full of secrets waiting to be uncovered. What other particles are out there? What other forces shape our cosmos? What new and beautiful laws of nature are waiting to be discovered? We don't know the answers yet, and that is the most exciting thing of all.